Our planet is a magnificent and serene portrait of beauty and power. Our planet is in continuous motion, spinning and revolving around the sun. The forces of nature are constantly reshaping our planet's structure, affecting all life forms in the sea and on land. Our planet provides natural resources that give us the environment and nutrients for healthy lives and the ability to enjoy many conveniences. Scientists are studying climate changes and continental shifts from the past 200 million years, collecting data to help predict what changes may occur in the future. Advances in technology are enabling researchers to read the record of Earth's history, preserved in seafloor rocks and sediments, in increasing detail, studying the planet over a great span of time, from millions of years to human time scales, learning how our planet responds to natural human influences. This is the work of the Ocean Drilling Program, an international consortium representing many countries that have joined together to explore the processes active on our planet. The Ocean Drilling Program is a cooperative undertaking unparalleled in the history of science, devoted to studying the planet's seafloor architecture. Governments are asking scientists worldwide to explore the ocean basins, which make up 70% of the Earth's surface, and to unlock some of nature's most mysterious secrets.
The program is looking essentially at answering the question, how does the Earth work? What makes it tick? What sort of things do we need to know to understand the Earth processes that will cause change?
We need to understand the oceans in order to understand how our Earth operates. And the Ocean Drilling Program, for an example, is very important in this because it is a way of obtaining a record from the ocean. It is our time machine that we can go back and look at the way the Earth operated in the past.
I think the Ocean Drilling Program is to the oceans what the Hubble telescope is to astronomy and space. It provides a capability to probe beneath the seafloor and to unlock the secrets that are contained within the sediments and the rocks below.
The Ocean Drilling Program is guided by the Joint Oceanographic Institutions for Deep Earth Sampling, or JOIDES. This is the international group of scientists providing the scientific direction and determining where the ship will drill holes into the ocean floor.
Many of the problems that the program addresses and that science addresses now are too big to be carried on by a single country. And it's this collaboration that's been an important product of the drilling program.
It's a culture of science, a culture of wanting to know and saying that in this program, it's the best science that will be done.
There are very few science programs that operate from the scientist up. There's very little government involvement. This is not a government agency, this is scientists.
The ship, a floating laboratory. That's the JOIDES resolution, named after the Ocean Drilling Program's governing body, JOIDES, and Captain James Cook's HMS Resolution, one of the first scientific exploration ships sailing during the 18th century. The JOIDES Resolution has 12 laboratories on board equipped with the latest technology, giving scientists the ability to research samples of sediments and hard rocks collected deep below the ocean surface. Scientists analyze and document their findings, which are transmitted by satellite to science operations at Texas A&M University. This information is used to develop reports and manuscripts that are published in scientific journals and textbooks. It is clearly the most advanced scientific ship ever to probe Earth's secrets below the seafloor. The JOIDES Resolution has sailed the world's oceans and seas, drilling for mysteries locked beneath the ocean floor for millions of years. A new knowledge of the ocean basins has given us a better understanding of the land masses of the world. For example, in the past 125 million years, the bottom of the Pacific Ocean has moved 2,000 miles north of the equator, colliding with another plate and creating the Aleutian Islands off the coast of North America near Alaska.
If you want to understand the Earth as a system, you have to know what's going on in the ocean. to understand the whole processes going on in such a big sphere needs integration of all disciplines of earth sciences.
The beginning of understanding the Earth and its changing state starts with understanding the environment beneath the ocean floor. For example, in the Atlantic Ocean at the Mid-Atlantic Ridge, a superheated cocktail of seawater and toxic chemicals hot enough to melt lead billows out of the sea floor. These fluids, driven by heat from molten rock below the sea floor, erupt into murky clouds that rise nearly 300 meters above the ocean bottom. Chemical reactions occur as the fluid mixes with cold seawater, forming chimney-like pipes called black smokers. These freestanding pipes, which commonly reach heights exceeding 30 meters, are known to contain minerals similar to those mined on land. On a practical level, ocean drilling program scientists are understanding the oceans as reserves of economic potential, determining how valuable minerals and hydrocarbons are formed.
We've discovered how mountains are built, how volcanoes form in the deep sea, how earthquakes occur. We're understanding some of the changes in global climate that have occurred over the last tens of thousands of years.
Some 65 million years ago, the Indian Ocean was characterized by vast volcanic chains of islands. At that time, the continent of India broke away from a huge supercontinent positioned over the South Pole, moved northward, collided with the continent of Asia, and created the Himalayas, the highest mountains on Earth. Samples collected from deep boreholes drilled into the Indian Ocean seafloor by the Geology resolution have provided important insights into the effects of mountain building on global climate. For researchers of the ocean drilling program, fieldwork means work at sea. Before scientists venture out to sea, extensive planning is done. Each site is selected with great care. The site itself is the object of intensive study by some of the world's leading scientists in this field.
The ocean drilling program is constantly coordinating an extensive number of cruises at any fixed point in time.
Once the site is identified, the ship's position is determined by the most advanced technology available today. An array of satellites forming the global positioning system is interrogated to report their position, allowing a computer on the ship to determine its position within 30 meters of the chosen drill site. Maintaining the ship's position in high seas is yet another challenge. A sophisticated system uses 12 computer-controlled thrusters to hold the ship steady over drill sites up to 5 kilometers beneath the ocean surface. The position system aboard the ship uses a hydrophone array that monitors the angle to a sonar beacon sitting on the ocean floor. Once the ship is in position, the drilling operation begins. Working around the clock, the rig floor crew assembles the drill pipe and lowers it section by section through the bottom of the ship. If a location requires re-entry to a hole, a 6-ton funnel-shaped instrument called a re-entry cone is attached to the drill string and set on the sea floor. The re-entry cone enables the crew to change drill bits, re-enter the same hole, and run casing or large steel pipe to deepen the hole. This is necessary because the Earth's crust is composed of many different layers of rock that vary in degrees of hardness. Each drill bit is designed to penetrate a specific rock hardness in the Earth's crust. Each time the bit is changed, the entire drill string must be brought up, pipe by pipe, strand by strand. With a new bit in place, the crew must reassemble the string before it re-enters the hole at the bottom of the ocean. Using the ship's dynamic positioning system, the crew guides the drill string back to the re-entry cone deep beneath the surface. A remote television camera and sonar help guide the drill string back to the hole. With a re-entry cone permanently in place, scientists can revisit the same hole years later. Investigating the unusual, daring to conduct operations in hostile environments, and challenging accepted theories is nothing new for scientists aboard the Geology's Resolution. Recently, scientists were drilling in an area called the Blake Ridge Carolina Rise, located along the coast of South Carolina in the United States. Scientists and technicians made unprecedented use of downhole sampling and measurement tools to characterize the phenomenon of gas hydrates.
Well, the Blake Ridge is probably the classic area for gas hydrate development. We believe that because gas hydrates have largely been inferred or detected on the basis of geophysical data. This is one of the first areas where gas hydrates were detected using these techniques, and it's probably one of the most extensive deposits of gas hydrate that we know of.
Science questions such as environmental effects of gas hydrates and its potential use as an energy resource can only be answered with ocean drilling. Back on the ship, the drilling continues. Now that the reentry cone is set on the seafloor, the crew is ready to lower the drill string through the moon pool. This large opening in the center of the ship has a tapered guide that controls pipe bending, so the pipe won't bend sharply as the ship rolls and pitches. The drillers ensure the operation is done with precision and care. While the drilling is in process, drilling parameters are continuously monitored to determine the progress of the drill bit. Once the drill bit wears out, the drill string is raised and the drill bit is changed. The entire drill string is rotated. The core barrel captures the cores of sediment as they are drilled, and the cores are pulled up through the inside of the drill string. They're all there, roustabouts and roughnecks, chemists and computer specialists, geologists, geophysicists, and paleontologists, people from many countries with many questions. It's a long, careful process, and then the moment arrives, the moment when the core sample is brought up, the moment when it's first examined by the scientists. Secrets kept beneath the ocean for millions of years. Superiorly equipped and completely integrated laboratories are aboard this ship. Here, the core samples are prepared, the first of a series of steps. Each sample, each step brings intricate details of science closer to an understanding of the Earth's history. The ocean floors are nature's way of archiving critical events during our planet's evolution. And while the cores are being prepared for detailed examination, the work continues on deck, the reaching down for new samples.
Unless we actually collect the samples that are going to allow us to solve the problem, we can talk about it forever. But as long as those samples remain locked under thousands of meters of water, we're simply never going to be able to address these problems.
The cores are cut in half. One half is stored in a permanent archive. The other half is examined immediately, subjected to a battery of tests, inspections, and examinations. The cores are examined internally with radiation for information not apparent to the eye, such as water content and magnetic properties. They are showered with sound waves that pass through the cores and provide additional important information on velocity, structure, and composition. They are checked for density, fluid chemistry, gas analysis, for color. All this information is integrated into a relational database and is used to decipher the paleohistory of the Earth. Special equipment photographs the core samples to fully document many properties, including colors, which will change over time. Let's take a tour of the core sampling process. It starts right here on the bridge deck, where technicians carry the 9.5-meter core from the drill floor onto a platform. Here they section the long, flexible cylinder in 1.5-meter lengths for easier handling and moves to each laboratory for analysis. Once the core arrives on the ship, paleontologists take a sample to determine the age of the microfossils, tiny skeletons of marine organisms less than a millimeter across.
In addition to that, paleontologists are trying to use the skeletal remains of plants and animals that used to live in the oceans for reconstructing the environment at the time of the sediment deposition.
Next, each section is taken into the core receiving station, where technicians record each section's length and the depth from which it was retrieved from beneath the sea floor. Physical property specialists then take the core samples and evaluate the physical characteristics of core material, using a variety of instruments to measure the changes that sediments undergo as forces bury them progressively deeper beneath the ocean floor. The process continues as paleomagnetists study the changes through time in Earth's magnetic field. The most dramatic change is a history of random reversals of polarity ranging from 50,000 to 30 million years. Layered deposits of deep-sea sediment and igneous rocks in the ocean crust record the magnetic changes. Now petrologists study the composition and characteristics of hard rocks and sediment. To aid in their analyses, they make optical thin sections from hard rocks or consolidated sediment to study under the microscope. Technicians slice thin sections from the rock with a diamond saw. They grind one side smooth and glue it to a glass slide. They then grind it as thin as a sheet of paper and polish it to a mirror-like surface. X-rays are used to examine and classify mineral structures. Each mineral exhibits a unique diffraction pattern. Sophisticated computer programs can search through tens of thousands of these patterns to identify various minerals. Geochemists study the core samples to determine the ocean's chemical composition and evolution. They make the most critical analysis when the cores are brought on board. Gas samples are retrieved to determine if the ship is inadvertently drilling too close to an oil or gas deposit, a process that is extremely critical when studying gas hydrates. The samples are injected into a gas chromatograph to reveal the quantity and quality of gases. Once all analyses are completed, the work half of the core samples are placed in the ship's refrigerated storage. Once the cruise is completed, both the archive halves and working halves are shipped to one of 4 repositories in the United States and Germany for storage and enabling scientists to further study the dynamics of the Earth's processes. The work aboard the Geology Resolution is intense.
Scientific party and the shipboard complement have a rhythm of 12 hours on, 12 hours off, and you can imagine how under the steady onslaught of core coming on board that it can get extremely tiring as the days wear on.
For 2 months you have nothing to do except sit there and work on your science, look at your samples, analyze those samples, and talk to other scientists about it. And it's incredible the synergy that happens when you put together scientists and you get that sort of interaction.
It's challenging, it's exciting, it's rewarding, so I really like it.
Life at sea during these expeditions requires people dedicated to finding the answers to scientific questions. Theories like plate tectonics. This theory helps provide a new understanding of the Earth and its history. In its simplest form, it says that there are giant plates, a dozen or so, that form the Earth's outer shell. Different sizes, different shapes, carrying continents and oceans alike. And they literally float on the much denser rock which lies below. The plates are in motion with respect to each other at rates that range from 1 centimeter a year to 15 centimeters a year. The plates interact at their boundaries, creating complex manifestations. When the plates come together, one may slide under the other, forming huge ocean trenches, spawning volcanic activity on land. Or they may crumple together and form mountains, as is the case of the Himalayas. How does this constant motion affect the planet's design and composition? Can this activity inhibit humans' ability to survive in what could become a hostile environment? Our planet's response to these questions and evolutionary change is sometimes violent and disruptive. Plates on the seafloor rubbing against each other, scraping against each other, resulting in huge faults and earthquakes. Plates moving apart from one another, causing crustal material to boil up to the surface and form what is equivalent to mountain ranges on the seafloor. The work of scientists aboard the Geology Resolution has provided some interesting findings that help us obtain a better picture of these massive movements and the consequences. The work of the ocean drilling program, like the processes it studies, is constantly evolving, unlocking the secrets of the forces that shape our planet, discovering unclassified species of life that thrive in sediment and rock below the seafloor, providing scientists throughout the world with valuable information to help understand global climate changes and natural hazards. Technology advances that enhance our ability to understand the global environment and allows us to be better stewards of the planet we live in, understanding the origin and evolution of life.
Most importantly, we need to drill deeper into the Earth's crust, at least 5 kilometres, if we're going to find the answers to the problems of what makes this planet work.
And I would maintain that the global ocean is this planet's last frontier, and it is appropriate that we commit the resources necessary to unlock its secrets and to understand its messages.
This is exciting stuff. I never lose my enthusiasm for this program.
This is the Ocean Drilling Program, studying our planet in motion.